When you think about acids and bases, we do break them down into strong and weak categories. So you can have strong acids and weak acids, and you can have strong bases and weak bases. Strong acids are acids that dissociate 100% into hydronium and some kind of counterion. So this is an example of nitric acid, HNO3. When nitric acid is mixed with water, which it almost always is, you really don't have any nitric acid at all. You have exclusively hydronium and nitrate. And I want you to focus on the arrow symbol right there. After our discussion of equilibrium in the last section, you might think this is an equilibrium, but strong acids, we will use the single arrow, and that just implies that all reactant is converted into product, and all strong acids and strong bases, for that matter too, dissociate 100%. So if you had 0.1 molar HNO3 solution, you would actually have 0.1 molar hydronium, H3O+, and 0.1 molar nitrate. There wouldn't be any HNO3 running around. So strong acids and strong bases dissociate much better than the weak acids and weak bases do.
When a few drops of water are added to solid calcium hydride, a violent reaction occurs that produces hydrogen gas.
If you're dealing with a strong acid or a strong base, the reactions are quite pronounced. All right? That's a hydride there, and hydride, when they react, oh man, there's a lot of energy given off. Scientists use acids and bases, like I said, a lot of times just for their energy properties. They convey energy to different things, and we'll look at this more in this area. I do want to point out again the hydronium ion. All right, hydronium ion is H3O+, and that's going to be something we're going to talk about a lot in this chapter. Hydronium is the hallmark of an acid. So acids will create hydronium if they're going to be acids. We're going to see that bases will create hydroxide, but acids give hydronium. So make sure you remember that.
When nitric acid, HNO3, encounters a water molecule, it forms an acidic solution by donating a proton, the H+ ion, to the water to form a hydronium ion and a nitrate ion.
So hydronium forms from acids. The acidic hydrogen in the acid gives up to water, and it ends up making this hydronium. Hydronium, we're going to see, is what makes acids acidic, all right? And we'll see that. Remember that with acids, almost always the acidic hydrogen is listed first. So HNO3 tells you it's an acid because H is listed first. That's not all the time the case, but I'd like it to be. But anyway, most of the time, if you have an acid, the acidic hydrogen is listed first. There are 5 strong acids, and I highly recommend that you memorize them / put them in your calculator or whatever you need to do. There are thousands of acids, but really there's only 5 strong acids that you need to worry about. These are 5 strong monoprotic, which means they give up 1 H+. And the 5 strong acids are nitric acid, HNO3, hydrochloric acid, hydrobromic acid, hydroiodic acid, and perchloric acid. And those 5 acids are very strong, all right? They dissociate 100%. We will use the single arrow when we're describing their reactions. We're not going to use equilibrium. That means that 100% of those acids will break down into hydronium and whatever the counterion is. You're going to see that if you know these 5 strong acids in Chem 223, then all of the other acids you'll run into basically will be weak acids, and that can be kind of important. So I do recommend you know / memorize those 5 strong acids. Weak acids are much more common than strong acids, and a weak acid is weak because unlike the strong acids, which dissociate 100%, most of the weak acids don't dissociate 100%. And a common example we talked about in Chem 221, and we'll look at again here, is acetic acid. Now, acetic acid, for whatever reason, is a lot of times abbreviated HOAC. OAC- is the the acetate ion. Acetate is one of the polyatomic ions we've been dealing with. But anyway, acetic acid plus water does have hydrogen transfer to make hydronium, and you have some acetate. But this is going to be now in equilibrium. All right, you won't have all of the acetic acid breaking down to hydronium, and usually it's much less than that. So roughly, if for acetic acid, it's like 1 of every 10,000 molecules will make hydronium, but the other 9,999 will stay as molecular acetic acid. So there's not the driving force for making hydronium in a weak acid that there is with a strong acid. So anyway, just realize we'll see acetic acid a lot. I will abbreviate it HOAC, and I'll sometimes abbreviate acetate OAC minus. You're welcome to draw them out as the full molecular version too, which is fine, but it is a common thing and we'll use it here in the future. Now, strong bases, like strong acids, dissociate 100%. Sodium hydroxide is an example of a strong base. It breaks down 100% into sodium ions and hydroxide ions. If hydronium is the way that you know an acid is an acid, hydroxide is the way that you know a base is a base. So every time you see hydroxide, that basically means that you're starting with something basic. There are 3 strong monobasic systems that I would recommend knowing. Sodium hydroxide, potassium hydroxide, and lithium hydroxide. So like with the strong acids, there's going to be thousands of bases, but most of them are weak bases, okay? There's only 3 strong monobasic systems that you need to worry about. And in this class, then basically all the other bases will be weak. There are other strong bases, absolutely, just like there's other strong acids, but they're not as common, okay? We're looking at the most common ones. So if you know the 3 strong monobasic systems and the 5 strong monoacidic acids, you'll be good to go. Calcium hydroxide is an example of a strong dibasic system. And in a dibasic system, you have 2 hydroxides to donate. And this is another strong base. It's not one that you need to memorize because we won't use it as much. A dibasic system means that there are 2 hydroxides to donate. You can have diacidic or diprotic systems, sometimes they call them, when you have 2 H pluses. Anyway, there's lots of other ones, but again, if you know the 3 strong monobases and the 5 strong monoacids, honestly, you're good to go for this class. Calcium hydroxide is especially interesting because it forms from lime. If you add water to lime, calcium oxide, it makes slaked lime, which is this calcium hydroxide. It's a really interesting system. A weak base, then, is just a base, something that creates hydroxide, but it's much less than 100% ionized. And in these kind of systems, you would use an equilibrium symbol. And one of the best known weak bases is ammonia, NH3, which we've been dancing around. Ammonia doesn't have a hydroxide in the formula. There's no oxygen at all. But when it reacts with water, it can make hydroxide, and that's what makes it a base.
Ammonia acts as a base in solution by accepting a proton from a water molecule. This liberates a hydroxide ion and results in a basic solution.
Remember that ammonia is NH3 and ammonium is NH4+. And the difference between those is the addition of an H plus to it. So when ammonia is in water, it makes ammonium and hydroxide. The presence of hydroxide is enough then to make this system somewhat basic. Again, there's literally thousands of weak bases. You do not have to memorize them by any means. However, do remember that there are 3 strong bases we'll run into a lot, and then basically all the other bases will be weak. It is cool to know ammonia versus ammonium. We'll run into those just like acetic acid and acetate will run into. Keep those in the back of your mind. Scientists wondered what was up with acids and bases for a long time, and there are many acid-base theories out there, but the theory that's used the most is called the Bronsted acid-base theory or the Bronsted-Lowry theory. And Bronsted and Lowry, as I understand, were 2 scientists working in separate places that essentially came up with the same idea. Bronsted was the first one to propose it. Lowry had been working in the basement, but he had notes and stuff. So anyway, unofficially Bronsted-Lowry, but most people call it Bronsted. Doesn't matter. I think scientists like that little O with the circle in it. I really think that's part of it. But anyway, we're going to talk here about the Bronsted-Lowry theory, or the Bronsted acid-base theory, and it's pretty chill. In the Bronsted theory, acids donate H plus ions and bases accept H plus ions. All right? So in the Bronsted theory, acids donate H plus and bases will accept the H pluses. And it's a pretty mellow thing, but with really good consequences for how these things all work out. So remember this, acids will give up the H plus and bases will accept the H plus. If we go back to the idea of ammonia, all right, ammonia is a base because it's accepting an H plus from water. And in the process, then you end up making ammonium and hydroxide. So in the Bronsted theory, it's not that the ammonia creates hydroxide, it's that the ammonia accepts an H plus from water. That's what makes it a Bronsted base. On the other hand, water is giving up an H plus to ammonia to make ammonium. So water here is acting as an acid. And that's kind of an interesting thing. We'll talk about more here in a little bit.
Ammonia acts as a base in solution by accepting a proton from a water molecule. This liberates a hydroxide ion and results in a basic solution.
Because ammonia is a weak base, we're going to use the equilibrium, the double-sided arrows. And again, ammonia is accepting the H plus from water, so that means ammonia is a base. On the other hand, water is giving up the H plus to ammonia, so it's acting like an acid, no problem. And in the process, ammonium, NH4 plus, and hydroxide are made. However, this is equilibrium. You don't have to think just about left to right. You can think about right to left too, because that's what these things do. They're literally in flux. It's dynamic, all that kind of stuff. So if you think about ammonium and hydroxide as your quote-unquote reactants, making ammonia and water as products, look what happens. Ammonium is donating an H plus, so it's an acid, and that H plus is being accepted by hydroxide, so it's a base. You can think about these as acids and bases from either side, either direction, and that's going to be a really interesting part. Finally, before we leave this, notice that ammonia and ammonium are related by an H plus. All right, you give the H plus to NH3, it makes ammonium. You take away the H plus from NH4 plus, and it makes NH3. Also notice that water and hydroxide are the same way. There's an H plus between them. Water's giving up H plus to make hydroxide. Hydroxide's taking an H plus to make water. This is an important part of acid-base theory we're going to see here in a little bit. NH3, like we saw, is a base in water because NH3 is taking an H plus from water. That's what a Bronsted base is. Water here is acting as an acid. It's giving up an H plus to make hydroxide. And sometimes when people start learning this, they think, oh my gosh, water is acidic. They like spit their water out or something like that. So first of all, acids and bases for that matter can be bad when you would touch them or drink them or something like that. However, most of the foods we eat and drink are actually acidic. And most of the cleaners that we use in our houses, most of those are actually basic. So moderate levels of acid and base are totally fine for our bodies, all right? You don't have to spit out the water. We're going to see water has some other interesting properties here coming up in a little bit. But I want you to realize that acids and bases are just terms, and they're nothing to be feared. Our bodies have totally adjusted to moderate amounts of acid and base, and it's no problem at all. But we'll see here that water is especially interesting. A conjugate pair is a pair of chemicals related by an H plus. So in the last slide, I mentioned how ammonia and ammonium are like related by an H plus, and so are water and hydroxide. If you have two chemicals that are related by an H plus, like one would give up the H plus and the other one would accept the H plus, we're going to call them a conjugate pair. So ammonia and ammonium are a conjugate pair. One of them will be the base, base, the thing that takes the H plus, and the other one will be the acid, the thing that gives up the H plus. And if you're uncertain which is which, the species with more hydrogen will be the acid, and the species with less hydrogen will be the base. Water and hydroxide are also a conjugate pair, and we're going to see that every acid has a conjugate base, and every base has a conjugate acid. This is a real wild part of acid-base theory. And again, because this is equilibrium, we can think about it as going back and forth, back and forth. It's going to create some really interesting things coming out. Here's hydrogen carbonate. Hydrogen carbonate is a weak acid, all right? It reacts with water. It makes hydronium, because acids should be creating hydronium somewhere or another, just like bases will create hydroxide, and carbonate. But now what you can see is, you can see now where the conjugate pairs are, all right? And remember, a conjugate pair is always an acid and a base, and they're related by an H plus. So hydrogen carbonate on the left and carbonate on the right, those are a conjugate pair. The hydrogen carbonate gives up the H plus to make, and the base will take the H plus to make hydrogen carbonate. Water and hydronium here are also a conjugate pair. Water here is going to take the H plus to make the hydronium, so that's when the water is acting like a base, and hydronium will give up an H plus to make water, so it's acting like an acid. Hopefully, though, you're seeing here that, whoa, water was an acid on the last screen when it was reacting with ammonia. Here, it's acting like a base. It's reacting with hydrogen carbonate to make hydronium. Water can be both an acid and a base. Here's a question you might run into. It says, which of the following is not an acid-base conjugate pair? Okay, and an acid and base conjugate pair is going to be related by an H plus. So one of them will have an extra H plus, and the other one will be missing an H plus. We've already seen that E is a conjugate pair, nitric acid and nitrate. We saw that earlier. But anyway, you take away an H plus from nitric acid to make nitrate. You add an H plus to nitrate to make HNO3. And you can see that most of these are conjugate pairs. This one has 2 hydrogens and this one has 1. That's carbonic acid on the left and hydrogen carbonate or carbonic acid on the right. HNO2 nitrous acid and the nitrite ion, that's another conjugate pair. Hydrofluoric acid, fluoride, etc. However, A up there, HClO and Cl minus. If you took an H plus from HClO, you would have ClO minus, the hypochlorite ion. And the hypochlorite ion is not the same as chloride. So A is not an example of a conjugate pair. You can't just add or subtract an H plus to make one into the other. Cl minus and HCl would be a conjugate pair, and HClO and ClO minus would be a conjugate pair, but that extra oxygen is enough to make them not conjugates. It's only plus or minus an H plus ion.